So I'm going to continue chapter 4, which is two-dimensional shapes. Hopefully I won't need a protractor again. I do not. I still don't have one. Polygons. A polygon is a shape with 3 or more straight sides. To calculate the angle sum of a polygon, split it into triangles. For the 5-sided polygon in figure 4.31, choose any vertex and draw as many diagonals as you can from the vertex, in this case 2, splitting the 5-sided polygon into 3 triangles. The sum of a triangle is 180 degrees. So the angle sum of 5-sided polygon is 3 times 180, or 540. In general, the number of triangles into which you can split a polygon in this way is 2 less than the number of sides of the polygon. The table shows the angle sums and the names of some polygons. Okay. A polygon whose sides and angles are equal is called regular. You can find the size of each angle of a regular polygon by dividing the sum of its angles by the number of its angles. Be careful when a question says pentagon, it means a 5-sided shape and not necessarily a regular pentagon. Okay. Okay. Interior and exterior angles. So far, in your study of polygons, the angle you have been given or have had to find have been inside the polygon. These angles are called the interior angles. If you extend a side, as in figure 4.32, the angle outside of the shape is called an exterior angle. There is a surprising fact about the sum of the exterior angles of a polygon. Suppose that you are walking around the polygon starting from A and facing B. Okay. Walk to B. And when you get there, turn from the direction BP to the direction BC. Now walk to C, and when you get there, turn from the direction of CQ to the direction of CD. Continue in this way until you come back to A, and you turn from AT to face B, and you are back where you started and facing in the same direction. On the way, you have turned through the angle equal to the angle sum of the exterior angles, but you have also turned 360 degrees because you are facing the same direction as before. Moreover, this argument applies to any polygon, not just the pentagon in figure 4.32. Therefore, the sum of the exterior angle of any polygon is 360. This fact is often useful in questions involving regular polygons because the exterior angles of a regular polygon are all equal. In figure 4.32, you can see that the interior angle and the exterior angle of the polygon lie on a straight line. It follows that at a vertex, the exterior angle plus the interior angles equals 180. Work out the size of each exterior angle and each interior angle of a regular pentagon. A regular pentagon has 5 equal exterior angles, whose sum is 360. So each exterior angle is 360 divided by 5, so 72. At each vertex, interior angle plus exterior angle equals 180. Thus, every interior angle is 180 minus 72, so 108. The size of each exterior angle of a regular polygon is 24 degrees. Calculate the interior angle of the polygon. How many sides has the polygon? Okay, let's actually draw this out. And in fact, I'm going to write these down. So 4.5 polygons. So divide polygons into triangles, and then times number of triangles by 180 to get angle sum of polygon. Right? And then 4.6, interior versus exterior. So exterior angles always add up to 360s. 360. So for example, a polygon, a pentagon is 5 sides, right? So if you have a pentagon, 1, 2, 3, 4, 5. So you have a pentagon. And the exterior is 360. So 360 divided by 5 sides is 72 degrees. And then to get the interior, you need to do 180 minus 72, which is 108. So the size of each exterior angle of the regular polygon is 24 degrees. So this is example 4.6.2. So the interior angle of the polygon, the exterior is 24 degrees. So 180 minus 24 equals what? $180 minus 24, 156 is the interior angle. How many? I don't know. The sum of the exterior angles is 360 and each exterior angle is 24. So the number of sides is 20. Yeah, 360 divided by 24 is 15. So it's a 15-sided polygon. So exercise 4.4. In questions 1 through 3, work out the sizes of the angles marked with letters. Okay, so number 1, A equals what? How many? 1, 2, 3, 4, 5. 540 minus 97 minus 123 minus 102 minus 92. So A equals, because I looked at so I did that by counting the sides, which is 1, 2, 3, 4, 5. And then I looked at the table. And I know a pentagon, the number of angles is 540. So 540 minus 97 minus 123 minus 102 minus 92 is 126. So A equals 126. 2. One, two, three, four, five, six. 1, 2, 3, 4, 5, 6. So 6-sided is hexagon, which is 72. So B equals 720 minus 99 minus 117 minus 122 minus 101 minus 126. So B equals, oops, 720. I got my calculator app open on my phone. 720 minus 99 minus 117 minus 122 minus 101 minus 126, which is 155. So B equals 155 degrees. Question 3. How many sides does that have? 1, 2, 3, 4, 5, 6, 7. Oh, I have to come up with my own. Boo. Okay, so let's do 1, 2, 3, 4. 1 and 1, 2, 3, 4, 5 triangles. Okay, so 5 triangles. So it'll be 180 times 5, which is 900. So C equals 900 minus all of these numbers. So it's 132, 141, 129, 139, 135, and 97, which is 900 minus 132 minus 141 minus 129 minus 139 minus 135 minus 97 is 127. C equals 127. Question 4. Work out the sum of the angles of a 12-sided polygon. So, from what I can tell, the number of sides to number of triangles, it's always minus 2. So it'd be a 10 triangles. So it'd be 1800, right? The sum of the angles is 1800? 5? So work out the sum of the angles of a 15-sided polygon. So it's always 2 less, so 13 times 10 times 13 times 180 is what? 13 times 180, 2,340. Work out the size of each angle of a regular pentagon. 6. A regular pentagon, a pentagon. Work out the size of each angle of a regular pentagon. Pentagon has 5 sides. 1, 2, 3, 4, 5. We do that up here, right? Which would be 540. Work out the sum of each angle of a regular pentagon. Sum of its angles by the number. So it'd be 540 divided by 5, which would be what? 540 divided by 5, 108. So 7. Work out the size of each angle of a regular decagon. decagon is 10 sides. So it would be 1440 divided by 10, which is 144 degrees. 8. Work out the size of each angle of a regular 18-sided polygon. So it would be 16, which is the number of triangles, times 180, which is what? 16 times 180, which is 2,880. And then that divided by 18 is 160. Oh, okay, and then 9. The size of an interior angle of a polygon, the interior size of an angle of a polygon is 109. Work out the size of the exterior angle of the same vertex. So it'd be 180 minus 109, which is what? 171. 10. Work out the size of each exterior angle of a regular hexagon. Hexagon is 720 divided by 6, right? Hexagon is 6. So which would be 720 minus divided by 6, 120. And then it's 180 minus 120, which is 60. So the exterior angle of a regular hexagon is 60. 11. Work out the size of A, each exterior angle, and B, each interior angle of a regular 12-sided polygon. So a 12-sided polygon would be 10 times 180, which is 1800. Okay, and then (180) divided by 12 is 1800 divided by 12 is 150. So that it'd be the B interior angle. So A equals 30 and B equals 150. 12. The size of each interior angle of a regular polygon is 140. How many sides has the polygon? So each side of the interior angle of a regular polygon is 140 degrees. How many sides has the polygon? So that's the interior angle. Okay. So it would be 360 divided by 140. I think so. Wait, that can't make sense. 360 divided by 140. Okay, let's try this again. Oh, because it's interior. So it's 360 divided by 40. Because if the interior angle is 140, the exterior one is 40. So it'd be 360 divided by 40, which is 360 divided by 40 is 9-sided polygon. 13. The size of each interior angle of a regular polygon is 168. How many sides? So it's 180 minus 168, and then the answer divided by 360, which will be 180 minus 68 is 112. And then 360 divided by 112 is 3.2. That doesn't make any sense. Okay. The size of each interior angle of a regular polygon is 168. How many sides has the polygon? Well, look at the answers. Okay. So, exercise 4.4, 126, 155, 127, 1800, 2340, 108, 144, 160, 171. No, just 71. Right. Yes. 60, 30 and 150, 9 sides and 30. Each side's, okay, it's supposed to be 30 degrees. How do we get to 30 from here? $360 times 30. It's 1800. Okay, so let's try this again. Each side of it, the size of each interior angle of a regular polygon is 168. So 180 minus 168. 180 minus 168 is 12. Oh my God. 360 divided by 12. 360 divided by 12 is 30. There we go. 47. 4.7. Oh my God. Symmetries of regular polygons. You already know that an equilateral triangle, a regular polygon with 3 sides, has 3 lines of symmetry, and that a square, a regular polygon with 4 sides, has 4 lines of symmetry. Figure 4.33 shows the lines of symmetry drawn on regular polygons with 5, 6, 7, and 8 sides. In general, the number of lines of symmetry of a regular polygon and the order of rotational symmetry of a regular polygon are both the same number of sides. Okay? Congruent shapes. If you make a tracing of one of the triangles in figure 4.34, you will find that the tracing will fit exactly on top of each of the other triangles. The triangle in 4.34 are exactly the same shape and size and are said to be congruent. If you turn the tracing paper over and the tracing fits exactly on top of the triangle, that triangle is also congruent to the original one. So symmetries of regular polygons, number of lines of symmetry equals number of sides. Okay, 4.8, congruent shapes. Which are shapes, same size, and shape. Shapes other than triangles may also be congruent. So write down the letters. Exercise 4.5. Write down the letters of the pairs of congruent shapes in the diagram. I do not have tracing paper, so I'm just gonna guess things that look the same. Okay, so exercise 4.5. So I think A and E look the same. B and H. C and G. D and J. Or maybe L. No. E and A, F, and that's it. I think that's it. A and E, B and H, C and G, and D and J. Boom. Tessellations 4.9. Tessellations. Figure 4.36 shows how regular hexagons can fit together without any gaps and without overlaps. These honeycombs are an example of this. Shapes which fit together like this are said to tessellate, and the tiling patterns they make are called tessellations. Tessellate and tessellations are derived from the Latin word for the small square stones used to make mosaic patterns. Each interior angle of a regular hexagon is 120, so 3 corners fit together to make 360. Right there. Figure 4.37 shows how equilateral triangles tessellate. In fact, all triangles tessellate. Each angle of an equilateral triangle is 60 degrees, so 6 corners fit together to make 360 degrees. Regular octagons do not tessellate, but a combination of irregular octagons and squares will tessellate, as figure 4.38 shows. Each interior angle of a regular octagon is 135, and 2 of these corners fit together with a right angle to make 360. This does not guarantee that the regular octagons and squares will tessellate, but if it were not true, they certainly wouldn't tessellate. Spotlight. There is a wide variety of beautiful tessellations ranging from intricate Islamic mosaics to the work of the Dutch artist M.C. Escher. Figure exercise 4.6. Draw diagrams to show how each of these shapes tessellate. Show at least 6 shapes in each diagram. Isosceles triangle. I don't understand what it's asking for. Okay. What should I call it here? I'm very tired. Okay. Well, I've only been doing this for 26 minutes. I'll finish this up. Oh, and then I'm done. I'll finish this up. Okay. Draw diagrams to show how each of these shapes tessellate. Is there answers? Or do I just... It doesn't say. It doesn't show. Okay. So draw diagrams to show how each of these shapes tessellate. Show at least 6 shapes in each diagram. Isosceles triangle. So isosceles is this way. B. It's A, B, squares. Let's see, very easy. My parallelograms. What's a parallelogram again? B. Kite. Well, you get the idea. Question 2. Without drawing, explain why rectangles tessellate. Four sides of 90 degrees equals 360. 3. Without drawing, explain why regular nonograms, 9-sided polygons, do not tessellate. Okay, so a 9-sided polygon would be what? Why? Because a 9-sided polygon, the interior something to do with the interior angles being what? So the interior of a 9-sided thing is 40 degrees. Right? Does it explain why? Please tell me. $140. So 140 does not divide equally into 360. Yes. And then 4. Draw a diagram with at least 10 shapes to show a tessellation using a combination of regular hexagons and equilateral triangles. That's a hexagon. That's a hexagon. So basically I draw that and then boom, done. Explain without drawing why it may be possible to make a tessellation using a combination of equilateral triangles and regular 12-sided polygons. Then using a drawing show that the tessellation is possible. So a 12-sided polygon is 12-sided polygon so 12-sided polygon is what? I can do this. So 12-sided polygon, so it'd be 10 times, I think I did this one already, right? Or 1800. So 1800 divided by 12 is what? $150. And then equilateral triangles. $60. Because two 12-sided angles, right, is 300. And then one equilateral triangle is 60. So together it's 360. Plus, sorry, equals 30. So in theory, a 12-sided shape, right? So what is a 12-sided shape? 1, 2, 3, 4, 5, 6, 7. Oh, shoot. How did you even draw 12 sides? Google what a 12-sided polygon looks like. Let's do regular 12-sided polygon. Image. Okay, so that's what it's gonna look like. Oh my God. Okay, so let's do 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. And if we do them right beside each other, and then in there we would do how many triangles there? We'd have to do many triangles to fit into there. Okay. So that's chapter 4. Right? So let's review why it says that we can do it. Yeah, each interior angle of an equilateral triangle is 60 degrees, and of a regular 12 polygon is 150. So 60 plus 2 times 150 equals 360. Yes. 60 plus 2 times 150 is 360. So the two shapes might tessellate, and they do. And they do. It's just very complicated. All right. That was chapter 4. We'll be moving on to decimals next time. Thank you for joining me.